Okay, Gen Chem, we are going to do a new chapter today. We are going to talk about chemical bonding today, and we are going to layer in some of the concepts that we have learned previously. So I just want to review the difference right now between ionic bonds and chemical bonds, or sorry, not ionic bonds and chemical bonds, ionic bonds and covalent bonds. So let's name the type of bond that we have when we form between atoms when they share electrons. Can you remember? When they share electrons, we create a covalent bond. Not band, bond. Not an A there. So remember, co means with or together, and valent means valence electrons. So we are sharing valence electrons between two atoms when we make a covalent bond. All right, let's name the type of bond that is formed when atoms transfer electrons. If I transfer electrons, do you remember? If I transfer electrons from one atom to another, I make an ionic bond. Because if I transfer electrons, that means one atom has more electrons than it should, and the other has less electrons than it should when it's neutral. So we make ions. Okay. Remember, when we make ionic bonds, the metal transfers electrons and becomes positive because it gives electrons away. And, whoa, what happened here? The metal gives the electrons away, and it gives the electrons to the nonmetal. And therefore, the nonmetal has a few extra electrons and becomes negative. Okay? Let's define electronegativity. We did that a bit ago as well. Electronegativity is a relative strength or attraction that an atom has for electrons in a bond. Okay, so we are going to see how strong an atom has for an attraction that an atom has for electrons when that atom is in a bond. Some atoms will attract the electrons more than other atoms. And because some atoms attract those electrons a little bit more than the other atoms, they end up having more of a share of those electrons than the other atom that they make that bond with. It's kind of like a tug of war between those two atoms. Who gets the electrons? Okay, so we're going to do a couple of just thought experiments here. So if I have this next section, if I have a sumo wrestler, and I have the diary of a wimpy kid, and they're fighting over a tug of war, who's going to win? Okay, hopefully you said the sumo wrestler is going to win. The sumo wrestler is a little bit stronger. Okay, let's do another scenario. If I have two sumo wrestlers that are equal size and equal strength, who's going to win in a tug of war between those two? Hopefully you came up with no one's really going to win. It's going to be a tie, right? No one really wins. They're going to share that rope equally. Or in this case, we're talking about electrons. They're sharing those electrons equally. What about this next scenario? If I have two equally weak individuals, like the Diary of a Wimpy Kid person, aren't they going to also come up with a tie? Yep. No one's going to win here either. They're going to have a tie as well. Okay, so we're going to use the electronegativity chart to see which atom ends up having more or less of a share of electrons when they make a bond together, or if they're equally strong, they're going to share those electrons evenly and it will come out with a tie. Okay, so to do that, we use this chart right here. This is our electronegativity chart. And notice we have a trend here where the upper right-hand corner are our most electronegative atoms. We actually have values on this chart, and we're going to use this chart a lot to use these values to determine what's going on with our electronegativity when we make bonds. So let me talk about this chart a little bit more. An atom that shares electrons with another behaves similarly. Okay, so we're going to compare these atoms and see what kind of a tug of war we have going on. Those atoms that win the tug of war for electrons are said to be more electronegative. Oh, I can't spell this morning. Okay, so the more electronegative an atom is, the more it is going to pull those electrons towards it. Okay, this is the general trend. So up here in the upper right-hand corner, we have our highest electronegativities. Now, when we talk about electronegativities, the noble gases do not have electronegativities because they do not make bonds. They do not react. And down here on the lower left-hand corner, we have our lowest electronegativities. Notice it's the same trend as ionization energy as well. I wonder why that is. Do you think you could figure it out? Okay, here are actual electronegativity values. We are going to use this chart a lot. And here's my question, and I told you this just a few seconds ago. Why do you think the noble gases do not have any electronegativity value? Think about that for a sec. Remember when we defined electronegativity? Electronegativity is all about attraction of electrons within a bond. Do these guys bond? Do the noble gases make bonds? No, they don't react. So because they don't make bonds, they don't have electronegativities. They don't make bonds, so they have no electronegativity values. Because remember, an electronegativity value is based on the relative attraction within a bond. Okay, so we're going to use this chart a lot. So you're going to want to keep this chart handy. Okay, I'm going to scroll back and forth. Okay, now we're going to determine the electronegativity value for each element in the bonds below. And then we're going to find the difference. Mathematically, what does it mean when I want the difference? Yes, I'm going to subtract. Now, when I subtract the difference between each atom's electronegativity value, we're going to take the absolute value of that number, okay? We don't have negative differences. We're always going to use the absolute value of those differences, okay? All right, so we're going to look on boron here, and we're going to look at chlorine. So let's look at boron and chlorine. Okay, so boron, right here, we have 2.0, and chlorine, we have 3.0. So let's look at that difference. Oh my. So boron is 2.0 and chlorine is 3.0. So the difference here, and I'm going to just use the little triangle sign, delta. Delta, that triangle sign, means difference or change. And so instead of writing it out all the time, I'm going to just write delta. So the change between those electronegativities of these guys is 1.0. Okay? Now oxygen, let's look at oxygen. Okay, oxygen is 3.5 right here. So 3.5. So 3.5 and 3.5. So 3.5 minus 3.5, our electronegativity difference here is 0. Okay, we're going to look at beryllium and fluorine. So if I look at beryllium, I've got 1.5 and fluorine is 4.0. Okay. So 1.5 and 4.0. All right. So I want the difference here. Now, if you want, you can always start with a 4 because it's larger. So 4 minus 1.5 gives me 2.5. So my difference there is 2.5. Okay. Potassium is 0.8 right there. Okay, so 0.8. And bromine, let's see, 2.8. So 0.8 and 2.8. So our difference here is 2.0. Okay, carbon and hydrogen. Let's look at that. Carbon's 2.5 and hydrogen is 2.1. So 2.5 and 2.1. So the difference here is going to be 0.4. All right, sulfur and oxygen. Let's look at those. So sulfur is 2.5 and oxygen is 3.5. So 2.5 and 3.5. 2.5 and 3.5. So our difference here is 1.0. Okay. Phosphorus and iodine. Let's take a look at those guys. Okay, so phosphorus we have 2.1 and iodine we have 2.5. So let's put those values down there, 2.1 and 2.5. Okay, so the difference here is 0.4. Let's see, aluminum and fluorine. I think we've already looked up fluorine. So let's look up aluminum. Okay, aluminum, we have 1.5 and fluorine is 4.0. So 1.5 and 4.0. Oops, I want that pen. 1.5 and 4.0. The difference here is 2.5. Okay, silicon and hydrogen. We already looked up hydrogen. Hydrogen's 2.1. Let's look up silicon. Okay, silicon, we have 1.8. All right, 1.8. So the difference here between 1.8 and 2.1 is 0.3. And last but not least, we have oxygen and nitrogen. So we've already looked up oxygen. Oxygen is 3.5. Let's look up nitrogen. Okay, nitrogen is 3.0. So 3.0. So our difference here ends up being 0.5. Okay, so we're going to learn how to use these values here. Generally speaking, if we have an electronegativity difference greater than 1.7, 1.7 or higher between atoms sharing electrons, they really don't share electrons anymore. We have an ionic bond, which means the electrons are transferred. They're transferred to the more electronegative atom. And the less electronegative atom loses the electrons. If I have an electronegative value of 1.7 or lower, it's said to be covalent, meaning we're sharing the electrons. But there's two types of covalent bonds. There's polar covalent bonds and there's non-polar covalent bonds. So let's do that scale really quick. Now, if I have a polar bond, my electronegativity difference is going to be somewhere in between 0.4 and 1.7. Polar just means that I'm not sharing the bonds or the electrons evenly. That means the more electronegative atom has more of its fair share of those electrons. Okay, so if it's polar, that means that the more electronegative atom has more of its share of electrons. And if it has more of its share of electrons, that means that end of the atom becomes partially negative. And the less electronegative atom, therefore, because it has less than its share, the less electronegative atom, because it doesn't have its share of electrons, becomes partially positive. Because we have partial positive and partial negatives, that creates poles like a magnet, a positive pole and a negative pole on that molecule. That's why we call these molecules polar, because they have poles. Okay, so we're going to decide on each of these bonds that we have up top, whether it's ionic, polar covalent, or non-polar covalent. Okay, so we're going to look at these electronegativity differences that we have created. Okay, ionic bonds, just to give you a heads up, are generally between a metal and a non-metal. Covalent bonds, on the other hand, are generally between two non-metals. So if you remember on the periodic table, do you remember putting that metal to non-metal dividing line? Should we put it in really quickly? Let's put it in on this table right now. And I'm going to put it in a bright red color. Okay, that metal to non-metal dividing line is right there. Okay, over here we have our non-metals. Oh, that didn't work. We have our non-metals. And over here we have our metals on this side of the line. The exception, of course, is hydrogen. Hydrogen is a non-metal. Okay, so now that we've got that put in, we're going to look at our bonds here. Okay, so we're going to look at these electronegativity values, and we're going to see what kind of bonds we have going on here. So we have an electronegativity value on A of 1.0. So if we look at the values that we have, nonpolar covalent has a difference of 0 to about 0.4. Polar covalent is about 0.4 to 1.7. And ionic is 1.7 and greater. So we have a difference of 1.0 here. So that means that we have a polar covalent right here. On B, we have a difference of 0. So this is going to be covalent. It's going to be nonpolar covalent. B, or beryllium and fluorine, we have a difference of 2.5, which is definitely bigger than 1.7. So this is going to be ionic. Okay, I want you guys to use that scale of 0 to 0.4 for nonpolar covalent, and 0.4 to 1.7 for polar covalent, and greater than 1.7 for ionic, and fill the rest of these in. Pause for a second and we'll come back. Okay, you ready to check? Okay, so here on D, our electronegativity is greater than 1.7. So this is going to be ionic. And then E, we have an electronegativity of 0.4. That's right on the cutting line. So there are a lot of people that would call this nonpolar covalent. And there are some people that would say that that's starting to be polar. Now, this scale is relative. So I would really accept both. Okay. F, we have a difference of 1.0. That is definitely a polar bond. Okay. G, we have a difference of 0.4. So once again, this is right on the line between nonpolar and polar. So I would accept either there. H, we have a difference of 2.5. So that is definitely ionic. Okay. And I, we have silicon and hydrogen with a difference of 0.3. That is going to be a nonpolar covalent. And J, we have a difference of 0.5 between nitrogen and oxygen. So that is going to be a polar covalent bond. All right, how did you do? All right, now let's look at all the different bonds and make them a list here. Okay, let's do a couple concepts first. Whenever electrons are shared unequally, remember we have a 0.4 to a 1.7 electronegativity difference for this. This is called a polar covalent bond. Okay, polar meaning that we are sharing those electrons unevenly, so we get a partial negative on the more electronegative atom, and we get a partial positive on the less electronegative atom. Whenever electrons are shared equally, remember our electronegativity difference here is 0 all the way up to about 0.4. This is going to be a non-polar covalent bond. Okay? Do we have any non-polar bonds up there? Let's look at the ones that we have labeled non-polar. Okay, so let's look at A. We labeled that polar. B, we labeled non-polar. So oxygen and oxygen. So B is one of them. Let's look at see if we can find the rest. Let's see, C is labeled ionic, D is labeled ionic, E is right on the edge. So should we put it in there? I think we should. E, and I'm going to put a question mark on it because it's right on that edge. Okay, F is polar, G is non-polar, but it's also right on that edge. So we're going to put a question mark by it. H is ionic, I is nonpolar. Okay, so those are the nonpolar bonds. Let's look for the polar bonds. Now, before we even look for the polar bonds, I can put E and G there because they are both right on that edge. Some people would consider them nonpolar. Some chemists would consider them polar. It's kind of a sliding scale. It's up for interpretation. Okay, let's look for our polar bonds. Okay, so A is definitely polar. Okay, so we're going to put A down there. Whoa. A is polar. Let's see. B is nonpolar. C is ionic. D is ionic. E we already have down there. F is polar, so we're going to put F there. A, F, E, and G.
I can learn to understand you.
Let's see. And J. J's polar. Now remember, these two are right on the border, so they can be either way. Okay? Let's look and see if we can find the ones that are ionic. Okay, ionic. Let's see. A's polar, B's covalent, C and D are ionic. So let's put C and D down there. It doesn't want to move. So C and D are ionic. Okay. Let's see. E is nonpolar, polar, polar. H is ionic. So we're going to put H there. Okay. So just based on electronegativity, we can determine if we have polar, nonpolar, or ionic bonds. Now I want to look back on C, D, and H and verify that they are indeed metals bound to nonmetals. So let's look at C. We have beryllium and fluorine. Yep, we have a metal. We look at beryllium. Beryllium's a metal, fluorine's a nonmetal. That works. And then K, potassium and bromine. We definitely have a metal here, potassium, to a bromine, nonmetal. And then our last ionic one, we have aluminum bound to fluorine. So let's check that one. Yep, aluminum's right there on the edge, but it's still a metal bound to fluorine, which is a nonmetal. So that relative scale of electronegativity differences does a fairly good job of determining whether we have ionic, covalent, or polar bonds. But once again, it is a relative scale, so there are things that it doesn't completely catch, but it does a good job about 90-95% of the time. All right, have a good day, and we'll have some practice of this exact type of stuff on your homework. We'll see you later. Bye.